Hey, test. So cool, let's start. My name is Flavio Brasil, and this is the Don't Block Yourself talk. It's a talk about Finagle and how Nonblocking IO helps you to build scalable applications. I know that I'm probably one of the last things between you and beers, so I will try not to be so boring. Who am I? I work as a backend engineer at SoundCloud. SoundCloud is a startup based in Berlin, so Berlin is a hipster city, right? So this is the hipster version of me over there. And I'm also on Twitter, and I'm also on GitHub. I actually started doing Scala some years ago through open source projects. So since then, I've been publishing some projects. Some examples here. So there is Clump. There is a free monad for service composition. Activate, a persistence framework based on a distributed durable software transactional memory. S-Mirror, there is a sane Scala reflection. API, Bond, a type-level validation library, and Zoot, that is a way of defining REST APIs using Scala traits, both for clients and servers. So SoundCloud is the world's leading social network for audio. We have 12 hours of new content being uploaded to SoundCloud per minute, 350 million users using SoundCloud per month, and our user base is not limited to Earth. We have one outer space user. So this is a really good reason to start using SoundCloud because Chris Hadfield posted how the toilet flush sounds in space. So you definitely should follow him and see how toilet flush sounds in space. We started out as a Ruby on Rails monolith, as many other startups, and we are migrating to microservices. The first try was using multiple languages, but nowadays we are doing mostly Scala, and Finagle was the library that we chose as the basis for this microservices architecture in Scala. Finagle is a library from Twitter, and it's a protocol agnostic RPC library. I will talk in details during the talk about Finagle. So this talk has three parts. The first one is about non-blocking IO. The second one about futures and promises, and the third one, the last, is about Finagle itself and the abstraction of building a server as a function. So part one, why non-blocking? If you start using SoundCloud, this is the page that you see when you are logged in, and there's a feature that we call stream. So it's basically where you can see the actions of people you follow at SoundCloud. It's similar to Twitter's timeline, for instance. And as we are using the microservices architecture as the backend for this stream endpoint, when we open our browsers, there is one request, and that is to the stream endpoint. And I was wondering how many internal requests to multiple microservices we have just to render a single response to the internet. So I found Zipkin trace. That is, Zipkin is a distributed tracing system, and Finagle has integration with it. And this is a trace of a stream request. And as you can see, we have a lot of lines. And each line here is actually one interaction between systems, between databases, microservices. And as you can see, it's like a lot of lines. If we zoom in, it's possible to see that this request took 320 milliseconds, used 22 microservices, and then 225 interactions between systems, network calls. So as you can imagine, we have a lot of requests coming from the internet, and each one of them translates into a lot of network calls internally. So, and the common approach to deal with network calls is more or less like this. You have, here we have like an interface, internet-facing API, and the timeline service that's responsible for the stream feature. And we have a request coming from the internet, some bytes over the network, and there's a thread on the API that starts processing this request. At some point, the thread sees that it is necessary to talk to the timeline service, so write some bytes to the network as a request, and then the very same thread stays waiting for the timeline's response. At some point, timeline returns, and then the API continues processing the request, maybe talking to other systems, and at some point writes some bytes to the internet as the response for the initial request. So this waiting situation, when there's a client waiting for a response or a server waiting for a request, is what we call blocking IO. And it is what is evil when we are talking about scaling applications with the JVM. Before continuing and talk about non-blocking I/O, I would like to add a parenthesis here. So this waiting time is actually really cheap. It's something that's like, it's not a busy wait as some people can think. It's something that's done without wasting a lot of CPU cycles unless you have a bug. And if you profile applications that are using blocking I/O, normally the profilers report the blocking I/O as using a lot of CPU, but they are wrong. Okay, so if this waiting time is something that is not expensive, why is it hard to scale an application using blocking I/O? It's because threads aren't free. If we have a lot of threads and scale based on threads, we have some problems because they have some cost. So I will talk about 3 things that make threads not free. So the first one is the fact that the JVM Java uses native threads. So this means that each thread that we have running in our JVM maps directly to a native thread on the operational system level. And this means that there are some resources associated to this thread. There are some other languages, other runtimes that have the concept of green threads or user space threads. That's not the case for Java. The second point is the fact that threads have execution stacks and they use memory. So if I scale an application for the case of SoundCloud where we have a lot of requests coming, we would need a lot of threads. So this means that we would have a lot of waste of memory. And the third point, and this is actually the most important one, because this is something that I didn't realize for a long time before I actually started understanding this when I started using non-blocking I/O at SoundCloud, is the fact that having threads generate garbage collection pressure. So it's because of the way that the garbage collector works, right? So where can we have, the garbage collector needs to know in order to clean up an object from memory if there are references to it. And where can we have references to objects? From basically 2 places. So the first place are the classes that are loaded. They can have static references to objects. And the second place are the execution stacks of threads. So if you have thousands and thousands of threads, you have a lot of execution stacks with a lot of references to objects. This means that you have much more garbage collection pressure. And it's even worse if you are using the hotspot VM, because at some point, the garbage collector needs to have a consistent snapshot of all references that are in execution stacks. So it means that the garbage collector needs to stop all threads and go through all execution stacks. And it's even worse if you have slow network operations. So for instance, if you have a request that takes 2 seconds, 10 seconds, you are holding a lot of references, and it's possible that the objects move generations and go to the old generation, for instance. And it's really hard to clean an object that's in the old generation. So cool. If we have this problem, what can we do? So there's this concept that comes from the telecommunication systems that is multiplexing. So the idea is reuse the same resource to do multiple things. Let's take this restaurant as an example. So there are some tables, some clients, and there's a kitchen over there. And there's a manager of this restaurant, and he thinks that instead of having 1 waiter, we should have 1 waiter per table. And then the waiter stays there waiting for a request, goes to the kitchen, and then stays there waiting for the food to be ready, and then brings some food back. Unless this is a really, really expensive restaurant, it doesn't make sense to be like that, right? Because waiters aren't for free. We have a price to pay if we have more waiters. And the solution is really simple, right? We can just have 1 waiter, and the waiter can go to multiple tables, collecting requests, go to the kitchen, deliver these requests, and then bring some food that's ready to a client. So this is what non-blocking I/O does. Instead of having threads waiting for network operations, we have some threads that stay there taking care of multiple channels, multiple requests, multiple network operations. So this is the non-blocking IO thread that is also known as the non-blocking IO event loop. But, okay, this is really cool. This allows us to scale better our applications. But there is a complication of this approach. When we use blocking I/O and we have this execution stack waiting for the network call response, we can see the request as it was synchronous, right? So because we can just resume the same using the same execution context, and if we don't have this waiting time. And then, like for instance, I can call timeline.stream and continue processing as a list of events because I have the execution stack to resume as it was synchronous. But if we don't have this waiting time, it means that we have to deal with the fact that network operations are asynchronous. So there are some approaches to deal with asynchronicity. So one of them is callbacks. So it's possible to call timeline.stream given a user and passing a callback that should be invoked when there is a response from timeline. But callbacks aren't too composable, they aren't too functional. We use something better that are futures. So I can call timeline.stream given a user and this returns a future of list of events. And this leads us to the second part of my talk, that is about futures and promises. What is a future? So a future has a type parameter, and it is a reference for an asynchronous computation completion. When I call timeline.string, it returns immediately a future of list of events. So I have an immediate reference for an asynchronous computation completion. So I can immediately have something that then I can use to compose new things. And to understand better how futures work, it's interesting to see how is the internal state of a future. So I'm talking here about the Twitter future API, and there is this method called pol, and it exposes the internal state of a future. So it is an option of try of the type of the future, in this case, list of events. And it is an option because at some point the future can be completed or not. Being not completed, it is none. Being completed, it's some. And being completed, it's a try, the result of the operation completion, because it can be a success, having the list of events, or it can be a failure, having the exception that made the asynchronous computation fail. And then we can use this immediate reference to do nice things. So it's possible to call timeline.string and then map the result and filter only the items that are track posts. And this gives us a new future that is the filtered future. So using future compositions, we can build our application without using any blocking operation. We can just use future composition and never use await, for instance. And then it's common to fetch something from a service and then go to another service. And you have two futures. Flatmap can helps you to bind these futures and compose a new future. And because the fact that futures are immediate references, if I call the authentication system and call the geolocation system, I have two immediate references and they are running in parallel, right? Because the futures are running asynchronously. So, and then we run things in parallel is really important when we are talking about a lot of network calls because we can reduce the overall latency of the initial request. And we can compose these parallel futures using some methods. So it's possible to use session.join geolocation, and this produces a new future that has a tuple of both futures. And then we can do something with this result in an asynchronous fashion. Another common pattern is having like a bunch of IDs and fetch all these IDs from a remote service. And then we have a collection of futures. So we can use the future.collect method to transform a collection of future into a future of collection. So this is like this pattern of fan out of request and then fanning of information to continue a future composition. And the future compositions are really powerful. We can express the same things that we do using synchronous code. So it's possible to define an asynchronous recursive composition. So this is a real example. From a service, I need to fetch all likes given a user. But I need to use the likes service, and this service has a hard limit on the number of items that it returns. So recursion is a good thing for this. We can continue the recursion until we don't have more things to fetch. So I first call the like service, given a user, and passing the initial offset of 0, and then I flat map to something. The result of the like service fetch can be a page that has next page, or a page that doesn't have a next page. So if we have a next page, we need to do the recursion, right? And if we need to stop the recursion, we can just use future.value. That is a way of producing a constant future. And to do the recursion, we can use the very same method. So I call likes given a user, but passing the next page offset. And the final step is a little bit more, it's a little bit trickier because there is an inversion of control when we are using futures. But basically, we map the final result to be the events of the current page plus the events of all following pages. That's done using the recursion. And another pattern, column pattern that we have at SoundCloud is fetching something from a service and then having to go to many other services to fetch a bunch of information about the things that we need to render. And this composition can be really expensive, and it can take a lot of time. So it's possible to define a timeout. So we can say future.within 2 seconds, and if the future doesn't return within 2 seconds, we have a timeout exception as the result of the asynchronous computation. And this is something that you can do using Scala futures, but the Twitter future implementation goes even further and implements something that's called cancellation. So if the initial future fails or has a timeout, all the downstream futures that were started by the initial future are canceled. So we just stop executing things that no one is interested in anymore. And the Twitter future does this within a JVM, and Finagle also extends this behavior over the wires, so it means that cancellations are also propagated between services. And this is really important because we can save resources, especially if we are running into an error path of our system. And it's even better when we are dealing with outages, because if I have a burst of timeouts and everything that was started by these requests continues to be processed, it's something that can overload our system because the clients can even start retrying and we have a lot of things being executed. So cancellation is a really nice feature of the Twitter future implementation. Another feature that the Scala futures don't have are local values. So when we create systems using synchronous code, it's common to use thread locals to hold some context about the execution of that's running, basically. And we can use for like holding the current transaction ID or the current database connection. And if we use Scala futures, and we can't use thread locals because the composition is running using multiple threads, right? So local values are a kind of thread local, but for asynchronous computations. And we can do something like this. So it's possible to have an object that has a request ID, and we have this composition calls service. The composition calls service 1, and then applies a transformation, and then calls service 2. And at any point of this composition, I can access the current request ID as we would be doing if we had thread locals. So I don't know how people are doing these kind of things nowadays using Scala futures. I've done something for my persistence framework using custom execution contexts. So, but it's not so cool. I think this is something that maybe should be added to the Scala future API implementation. And the last thing about futures are promises. For our Twitter futures, promises are really simple. They are futures, so they implement the future interface, but they are futures that you can create and at some point write the value of the future, the result of the computation. So yeah, I can just create a promise and then set the value. But this is something that shouldn't be common to use. It's more for more advanced usages. Like it's possible to implement future.collect using promises. It's possible to implement, transform a Java callback-based API into a future-based API using promises, but something for more advanced usages. If you have a lot of promises in your day-to-day code, be careful. Try to rewrite using plain futures composition, because it will be easier to understand, more composable, more functional. So let's go to the last part of my talk, that is about Finagle and how to build your server as a function. So Finagle is a library from Twitter, and it is a protocol agnostic RPC library. So RPC, there's some confusion about what is RPC. Here, it's basically, in this context, is basically an interaction between two systems using the network. So Finagle tries to, the abstraction is basically have a bunch of implementations that you can reuse and for multiple types of communications. So you can reuse the same connection pooling implementation to talk to MySQL, Memcached, Redis, you name it. And Finagle is based on a nice tripod of concepts that are futures, services, and filters. So we already know about futures, right? So let's not talk about it. Let's talk about services. So a service, it has this type signature. So it's from request to a future of response. It's a function, but it returns a future, so we can call it an asynchronous function. So Finagle uses this type signature to represent any system boundary. So if you have a client for a remote server, you have a service implementation. If you are implementing a server, you also implement a service, this function, basically. And so it provides uniform and symmetric API for clients and servers. And the last, so I have an example here. It's possible to have a client that is a service, and the implementation is calling a remote server, and then I can use the apply method, passing the HTTP request, and this returns a future of HTTP response, and the same type is used on the server side. So I can have a server that is a service implementation. It's the actual implementation of the service, and we can start a new server using http.serve to start and listening the AT part. And the services are so composable that it's possible to define a one-liner proxy using Finagle. So I can use http.serve passing the port, and the second input is the client to another HTTP implementation. So it's a proxy, right? I have a service that's listening to the localhost 80, and I can start a new proxy that will listen to other parts. So this is really cool, and this shows how composable services are. And the last concept are filters. So filters are similar to what we have for servlets, for instance, but they are basically asynchronous. So the inputs are request and the next service in the filters chain, and the result is a future of response. So we can use filters to implement agnostic concerns like timeouts, retries, authentication. This is an example of a timeout filter. So the implementation is basically forwarding the request to the next service in the filters chain and saying that the filter must return within 2 seconds. And then I can use this filter to compose new services. So I can say like new timeline filter and then service. And this filter is reusable in 2 ways. This is really interesting, really cool. The first way is because the types of request and response are not specific to a type of communication, I can use the same timeout filter to talk to Memcached, MySQL, many types of communications. And the second way that it can be reused is on both clients and servers. So you can build a client saying new timeout filter and then the client to a remote service, and all requests to this client should return within 2 seconds. And you can also build your server saying that using the filter and saying that all requests to my server should return within 2 seconds. So Finagle uses this concept of filters internally. This is a little bit more complex. There's this stack concept here that is basically like a configuration of stack of service factories and filters. But my point here is show you that even Finagle internally makes heavy use of filters to build a bunch of things like error handling, distributed tracing, a lot of things. And at SoundCloud, we have also a bunch of filters, both to do like infrastructural code and like timeouts, error handling, and to apply business rules as well. So they are really powerful to implement things in a really isolated way. But Finagle is not only this really nice tripod of three concepts that play really nicely between them. It's not a nice way of dealing with the complexity that Nonblocking IO introduces to our code base. Finagle has a bunch of features. So Finagle has connection pooling implementations, has load balancer implementations. We have almost for free distributed tracing if we are using Finagle, using Zipkin. It's possible to implement and integrate with many types of service discovery. There is built-in support for Zookeeper, and Finagle also provides metrics for a bunch of things. So as you can see, having these features is something that if you build something using Finagle, it means that you have most of the things that are necessary to maintain a production system. This is a really interesting characteristic. And I would like to talk about something that's really important, and this is probably the most important part of my talk, is the fact that Finagle is reactive. So you can start using it right now. So it has a bunch of failover strategies that you can use. It's possible to define failure detectors and configure them. It's possible to build a dynamic cluster using Finagle and service discovery. And Finagle also has back pressure. So it's possible to constrain the resources usage, and this applies, for instance, the number of concurrent requests or the number of connections, and this applies back pressure on the TCP level. And Finagle has another type of back pressure that's really cool. So there's this new protocol called MUX. It's really interesting, and it has a feature called GC avoidance. So when we are talking about scaling applications using the JVM, at least in my experience, one of the most complex things are dealing with the garbage collector. So basically, we will start having GC pauses, and this can lead to timeouts or errors. And GC avoidance allows us to deal with this problem in a better way. So how it works? Imagine that you are a client. Okay, and you have a set of instances of a server that you can talk to. So you have like 100 servers that you can talk to, and at some point you can send a request to a server, to one instance, and it can be running GC cycle, so probably the request will have higher latency or maybe fail. So wouldn't it be really nice if the server, before starting the GC cycle, says to you as a client, hey, yo, please stop sending me requests because I'm going to run a GC cycle. So this is what GC avoidance does. It's really simple. It's like a really elegant solution for something that's really complex when we are talking about scaling applications with the JVM. But to be honest, I've been trying to use GC avoidance at SoundCloud, but it's not working really well outside of the Twitter's custom JVM because they have a custom JVM with a custom garbage collector, and Finagle is capable of forcing a minor GC using this custom garbage collector. And if you are using the hotspot VM, as we do at SoundCloud, it forces a major GC collection. So yeah, it's not so good. But I'm still using MUX because it's a session layer protocol that uses a single connection between clients and servers, and it also has some nice features. And the latest version of Finagle has a new failure detector for MUX, and I was having problems with garbage collection, constant error rate because of timeouts when a server was running garbage collection. And at some point, I started using this new version of Finagle and configured the failure detector. and I was able to reduce almost to zero the number of errors because of garbage collection. So yeah, it's something. This failure detector works more or less like this. It continuously pings the targets, and if there is a target that has a higher latency for pings, it just assumes that it is running a GC cycle. So I've been working with Finagle for almost 2 years at SoundCloud, and I would like to share some conclusions about my experience. If someone's trying to sell something, technology stack, saying that there aren't problems, be careful. That's not different for Finagle. Finagle also has some problems, and I would like to talk about them. So you can't use Scala futures directly. So sometimes you need to talk to Finagle and also to other libraries using Scala futures, so it can be tricky. It's not so good. The Finagle code base is slow to adopt new Scala versions. Finagle is still using NetE 3. The latest version, stable version, is NetE 4, and they are working on NetE 5. And NetE 3 has some problems in terms of performance and garbage collection pressure. So yeah, they are slow in upgrading dependencies. The internals are complex sometimes, so the outside, these three concepts, they are really nice and easy to understand, but sometimes you need to dig into the code base, and it can be more complex. And the MySQL driver, the protocol to MySQL, is not so good, but they are working on a new version. But overall, after 2 years using Finagle, I can say that I'm a happy user of the library. It's a really good toolchain. We can talk to many types of protocols. We can talk to MySQL, Memcached, Redis, HTTP, you name it. The community is very active, so you can just send an email to the mailing list, and the maintainers will answer really fast with really good and complete answers. So this is really cool. And we can also know that things coming from Finagle are battle tested. So they are using at a really high scale at Twitter, and we are also using at a really high scale at SoundCloud, and a bunch of other nice and cool startups are using Finagle. So don't block yourself. Thank you. So we have some time for questions. If someone, could you go to the microphone? Yeah.
Okay, so you mentioned that you were using Redis from Finagle.
Yeah.
And I was just wondering how you do the use of load balancing, because I tried to do it and it's working perfectly with one server, but once I activate Sentinel, it's only connecting to the right one, and the second operation is connecting to a slave and giving me an error. So what are you using? Load balancing, clustering?
Yeah, so Finagle, as I said, has some implementations for load balancing. So there are a bunch of load balancer implementations, and they are reusable for any kind of communication. So you can use it to talk to Redis or Memcached, and it's like something that's, you can even compose connection pools. So it's possible to have a watermark connection pool that is blocking, and on top of it have a buffer pool that's non-blocking, for instance. So it's something that is really configurable and flexible.
So you mentioned with Finagle you can basically share the models. So in that sense, are your services not really independent from each other, right? So how do you manage that?
Sorry, could you repeat the question?
So you are proxying basically the calls, right? So you're in essence sharing the models between the services, if I understand correctly. But in that sense, your services aren't really independent from each other, right? So how do you manage those dependencies?
So you're talking about the reusability of things like connection pooling and timeout filters, right?
Now, for instance, if you have, in one of your slides, you were making a call to an HTTP service.
Okay.
You get back an HTTP response, and that response model that was basically in the proxy object, so you're sharing that model, right? Or do I just
Yeah,
misunderstand?
but this is a model that Finagle provides, and like it's a library that you can import from many systems. So yeah, you can reuse these models.
Okay, but in that sense, your services basically are sharing this model, so they're not really independent, right?
Yeah, but this is a model like a HTTP request. It's a library model. It's something that it's not a business rule or a business object. It's something that Finagle provides, and it's something that you can use for any HTTP communication.
Okay.
Okay, it's not specific to our system.
Okay, thank you.
Pretty quick question about how do you ship your services? Do you use Akka microkernel or Zookeeper Service Factory for like deploying the whole cluster of your Finagle services?
Okay, so at SoundCloud, the way that we deploy our systems is using a custom Heroku system, similar to Heroku. So it's internal, it's not open source. And we can deploy many instances, and they talk to each other using service discovery. So if I scale like 100 instances of a service, I can discover all these 100 instances from any place. So I can, if I need to talk to a service, I can just use service discovery to find all targets. Any other questions? Cool. Thank you very much.